Well, let's talk about rational functions. Rational functions are just functions that are basically a ratio of polynomials. This is going to be the first of three videos about rational functions. This one is just going to discuss how to find the domain, x-intercepts, and y-intercepts of a rational functions. Rational functions can look very different on graphs. So you notice three possible graphs here on the screen. Typical rational function is it's about as simple as they get. We'll have a vertical asymptote here and a horizontal one. Again, we'll talk about those things in another video. But basically, you've got your hyperbola, right? The right part and the left part of this purple screen here. The vertical asymptote really shouldn't be showing up, but it's drawn in here. You could also have a rational function that looks much like the orange lines down here at the bottom, or possibly even three different parts or even more parts than that, like up here on the right. So again, rational functions can have a lot of different things going on. What we want to be able to do is find some of the major parts to help us graph. So we'll discuss the same three functions in all three of the videos. The first one of which is f of x equals x squared plus x minus 6 divided by 2x squared minus 9x plus 10. Now, to find the three parts that we're going to talk about in this video, the domain, the x-intercepts, and the y-intercept, basically, the y-intercept is probably the easiest one of the bunch, but we'll save that till last. The other two basically have to do with the numerator and the denominator sort of separately. And again, a polynomial divided by another polynomial, again, that's what we call a rational or a ratio of functions. It's a rational function because it's a ratio of two polynomials. The best thing to do to help us figure out the domain or the x-intercepts is to factor. So I'm going to think about the top and say what would add to the middle, add to 1x, but also multiply to negative 6. Well, very simply, x plus 3, x minus 2, if we distribute those together, or FOIL those together, if you're familiar with the process, that would construct x squared plus x minus 6. So we're going to take that apart. What that helps us figure out is, well, if those are the factors on the top of the fraction, right, then they're possibly x-intercepts. Okay, possibly x-intercepts. And we'll talk more about that in video 2, the fact that really one of them won't be. And you'll notice that's because on the bottom, when we factor, and notice it's a little trickier factoring, 2x squared minus 9x plus 10. Again, one simple way to think about that is 2 times 10. What would multiply to 20 and add to negative 9? That might help you get your negative 4 and negative 5. But in that case, remember that the front needs to be a 2x and a 1x. So again, that negative 4 will come from 2x times negative 2 here. Again, there's a lot of ways to factor that. So maybe talk to your teacher if you have any questions about that. They can maybe give you some tips or tricks, how to do that. Because that x minus 2 is sort of in common top and bottom, technically not going to be an x-intercept, but we're going to identify it as one for now. Basically, when we talk about the domain, though, we're going to talk about numbers that can't be used for x. Basically, the domain is the numbers that can be, but when it comes to a rational function, we're thinking about division. We're thinking about when would we end up dividing by 0. So what I'm going to do now is let's go ahead and do this. I'm going to take the factors that are on the bottom, and I'm going to set them both separately equal to 0. 2x minus 5 equals 0, or x minus 2 equals 0, which means that 2x equals 5, and x equals 5 halves. And basically, one number that can't be in the domain, right, of our function, because it would make the denominator into 0, right, like we noted here, would be 2.5 or 5 halves. So our domain, right, if we wrote it in, sort of an old-fashioned route, but if we just said all real numbers, as long as x is not equal to, right, our 5 halves, 5 over 2 here, right? Or, for that matter, because of this side, again, add 2 to both sides, we also can't be 2. Which is why when we go to do our x-intercepts, normally we would just say whatever can make the top 0. Well, we're pretty familiar with linear factors. So I'm going to say, looking at the top one, x plus 3, well, I would say that negative 3 is going to make the top of our fraction 0. And remember that 0 over anything is always 0. So if the top of our fraction equals 0, then we found an x-intercept, right? Then f of x was equal to 0, or basically it's going to be an x-intercept. Now, we could also technically, for now, identify 2, right? Because we've also got this other factor over here. We could also identify that 2 comma 0 would be an x-intercept. But the problem is, remember, we already said 2 can't be part of the domain. So that's why I would go ahead and cross that one out. Again, we'll have a different idea for that tomorrow or on the next video of why that is and what happens to our function when x equals 2. Finally, we can take our function, and again, to be a y-intercept, that means that x equals 0. So very simply, we're just going to plug 0 in. 0 squared plus 0 minus 6 over 2 times 0 squared, again, still 0, minus 9 times 0 plus 10, or basically negative 6, right, over 10 is going to be negative 3/5, right? Divide by 2. And basically we get a y-intercept of 0, negative 3/5. So again, the big things we're looking at for the domain, we just don't want the denominator to be 0. We can't divide by 0. For the x-intercepts, it's whatever makes the top or the numerator equal to 0. Because again, any fraction is going to have 0 over something, right? Very simply. Although we do need to be careful, whatever that is can't also make the denominator 0. And then finally, the y-intercept is whenever x equals 0. Let's go ahead and look at another example very quickly. Again, the first thing that we're going to want to do is factor that out, which might just mean, especially since the bottom is a cubic function right now, it might be easiest to take that denominator and graph it and find where all of the zeros would be. Right? Otherwise, you can try to factor by grouping if you want to, or there's lots of different ways to factor. But to find a way to factor that apart, again, what I did is I went ahead and graphed and just found that x equals 2, negative 1, and positive 1. Again, x equals 2, x equals negative 1, and x equals positive 1 were x-intercepts for the denominator, right? So I went ahead and factored it out that way. On the top, again, same idea as before, 2x squared meant I needed a 2x and an x, and then I sort of just worked out the foiling going on there. Again, I'm going to take my domain, and I'm going to say it can be all real numbers. Now, we could also write this in interval notation. So actually, I'm going to go ahead and change up my method here real quick. Let's think about interval notation, as long as we have them all written down here. It's going to be kind of a long one. But again, if we started from negative infinity, I can go up to negative 1, right? That'd be the first one I would run into. I don't want to include, so note the parentheses there. Don't include negative 1, but work our way up to positive 1, right? Not including positive 1. Work our way up to 2, not including 2, right? Skipping over 2. Don't forget those commas in between these intervals. And finally working our way up to infinity here, right? So again, you'll notice interval notation might get a little messy sometimes. Might be easier, as I mentioned, just to say all real numbers such that x can't be equal to, right? All real numbers being that R with the double bar, that single lettered symbol, that's sort of a double bar on the side, a set of numbers, all the real numbers not including 2, 1, and negative 1. Okay. The x-intercepts will be whatever makes the top 0. So maybe we'll do a little work here. 2x plus 1 equals 0. 2x equals negative 1. Therefore, x equals negative 1/2. Which would mean, again, and there's going to be an x-intercept at negative 1/2, 0. And we'll also have an x-intercept. Again, our other factor was x minus 1 equal to 0, which means x equals 1. But again, that also was, again, one of my numbers I can't use. So you could list it, again, for now. But again, tomorrow we'll take that out and we would say, nope, can't use that. Because again, it can't be an x-intercept if it can't even be in the domain. And then finally, the y-intercept. Again, I would just plug in 0 for this. All these terms, any term with an x in it. So again, all of these terms up top with x's are going to turn to 0. And we're basically going to end up with the constants of our function. Or basically, if I plugged in 0 for x, I'm going to get negative 1/2 right now. Let's do one last example very quickly. Again, the bottom is already factored. It's already just this linear factor, x minus 1. The top, would factor into the same idea. Multiplies to -2, adds to -1. Well, I'm thinking -2 and +1 work pretty well there. Right? Got a stray mark there, so let me get rid of that for us real quick here. Which means, again, whatever makes the bottom 0, so right now x being 1 would be an issue. So I'm going to say all real numbers such that x can't be equal to 1. Whatever makes the top 0 are going to be my x-intercepts, so +2, because again we've got an x -2 for a factor, and again -1 because we have a negative, or x +1 is a factor. Again, neither of those two x-intercepts this time would make the denominator 0, so they'd both be x-intercepts. They make the top of our fraction 0. 0 over anything is going to be 0. And then finally, again, for the y-intercepts, ignore any term that has an x in it, and I'm just going to be looking at, again, the constant part of my function here. -2 over -1 makes for a +2 when it comes to a y-intercept. Again, I hope that helps you finding the domain, the x-intercepts, and the y-intercepts of a rational function. If you have any questions, talk to your teacher. Otherwise, if you're looking for more information, again, feel free to view videos 2 and 3 discussing rational functions. They're going to talk a little bit more about the asymptotes and a little bit more about the graphing of a function, of a rational function. Have a great day.